Good morning, my dear JEE warriors. Welcome, welcome, welcome. All my 2026 students, the class 12 syllabus. Well, we are on to the chapter of magnetism, magnetic effects, magnetic sources. So, this entire unit starting today. Today, we are just going to do the Biot-Savart Law and its applications. Next class, we'll be doing Ampere's Law and its application, and so on and so forth. Then we'll go to permanent magnetism, magnetic effects like the Lorentz force will be a separate part. Okay, all those things will happen sequentially in separate classes in detail, right from basics, so that you not only understand the theory but also apply the concepts along with the PYQs, as you have seen in every single class. So all the concepts of Biot-Savart's law and its applications, like the wires and also the curved wires, basically the arcs or even the circular coils. That's what we are going to see today. Your solenoids, toroids, everything will come in the next class. Okay, right. This is your Captain Shreyas. Welcome. This is the first lecture of magnetism. Yes, Ibu, correcto. And quickly smash the like button if you have forgotten to do so, and subscribe to the Vedantu J English channel, which is your channel consistently doing every single class right from the month of June. If you remember, we started class 11th and class 12th syllabus, entire coverage, daily live classes for all of you, in-depth physics, chemistry, mathematics. Already 2 months done, June and July done. We are slowly entering August in the next couple of days. Welcome everyone. Nice to see all of you. And yeah, smash that like button down here quickly if you have forgotten to do so. Where is my like button has shifted, is it? It's here. Okay, great, done. Let's hit 100 likes. Hi Paki, hi Du, hi Tilak. Hello everyone, welcome aboard Bhubaneswar. Hi Biran, nice to see you all, right? And if you are looking forward for any kind of support, help in terms of coaching, I have put all the links in the description box, so please check it out, as you're watching or even after the video. Like the Sigma batch is there, which is the batch where your captain, your Diksha ma'am, Namrata ma'am, everyone are there, along with other sirs like PNJ sir and Pahul sir and everyone. And of course, you have the pro batches also. You can book a demo. That's the best way to check out how the pro batches are. And of course, you can check out our offline centers across 20 plus cities, right? So have a look at it. All the links are there in the description. Let's move to the concepts. Okay. So let's start with the Oersted's experiment. Let's start with the Oersted's experiment, which is nothing but proved that current can create magnetic field around it. So Oersted's experiment is all about the current produces magnetic field around it. Current produces magnetic field around it. That is what Oersted's experiment proved. All he did was use the compass like this. You might have seen a compass. Yeah, it looks something like this. Yeah, it points to the north, used by navigators and so many other, people. So if you take a wire which carries current and take this kind of a compass and place it here, it will start deflecting. And the closer the compass is, the deflection is more. The farther the compass is, the deflection is less. Also, it was found that if the direction of the current is reversed, that means the polarities were inverted, then the deflection also reverses. That means the direction of the current affects the direction of the field. It is exactly opposite if the current is reversed. All these things were clear by Oersted. He also used magnetic materials like iron filings. This is like a powder. Okay, these are small, powder like material of iron. Iron is magnetic in nature. So if you sprinkle them and you pass the current, then the iron fillings, because they are magnetic in nature, they align themselves in beautiful circles, which show that the magnetic field is also circular around the wire. Okay, so that is what basically Oersted said. So As per Oersted, the deflection, the deflection, deflection is higher. The deflection is higher near the wire, near the wire. What does this exactly tell me? The deflection is higher near the wire. It basically tells me the field, the magnetic field, the magnetic field, the magnetic field is stronger. The magnetic field is stronger when you are closer, when you are closer to the current element, when you are closer to the current carrying element. That is what it concluded. Another thing, like I said, the deflection reverses, the deflection reverses when polarities are inverted, when current inverts, when current reverses, when current reverses its direction, when the current reverses its direction. So that in turn proves that the direction of the magnetic field, the direction of the magnetic field is completely dependent on the current's direction, dependent on the current's direction. All these things were very, very clear. And of course, talking about the magnetic field directions or how they look like, the magnetic field lines, the magnet or basically iron filings, iron filings, they arrange themselves, they arrange themselves in loops or in circles around the wire, around the wire. What did this proved that the magnetic field, magnetic field is in loops, is in basically loops. That is what it proved. Till this point, absolutely clear? Yeah. For NSCP, a batch on YouTube, I don't think it is justified because you need a proper one-on-one kind of a thing. Although I will conduct problem-solving classes and I will take up some sessions for NSCP, but a batch per se, I think it is always better to be under the mentorship of the Eklavya teachers. I've already told you about it, so please check out the details. NSCP, there is a separate batch for 6,999 rupees or something. Yeah, it's a very small size batch with dedicated material, with dedicated test series, with dedicated discussion of the test series and separate concept teaching for NSAP. Okay, so I think that is the basic. I will do some classes for sure on YouTube, but that will not be the complete thing which you should depend on. That's what I would say. Vanakam Anirudh. Hello Tilak. Welcome everyone. Yeah, Abhiram, I hope that is clear regarding NSCP. Okay, but I'll definitely take up classes. Now, although Oersted experiment, proved that current can produce magnetic field, but what is the nature? What is the formula? What is the value? Is there a specific formula by which I can get the magnetic field? That was obtained by Biot-Savart's law. So they formulated, what is the field due to the current carrying wire. But before going there, I think we need to define one thing, which is the magnetic field, which is basically magnetic field. Now, this particular magnetic field, this definition actually comes in SI units later on. So right now we'll just accept it the way it is. Symbolically, it is nothing but B. It is not E. E is for electric field. B bar because it is obviously a vector quantity. It is a vector quantity. The SI unit of magnetic field is a Tesla. Yes, your Tesla car came in India recently, and I'm not sure how many of you are happy or sad about it. But there is also another unit which is not SI, it is Gauss. And one Gauss, it's a smaller unit, is 10 to the power minus 4 Tesla. 10 to the power minus 4 Tesla. The short form of Tesla will be capital T, like 10 Tesla, 5 Tesla, zero point 0.1 Tesla, like that. So Tesla is the unit of magnetic field. How much is a Tesla? To give you an idea, just to give you an idea, right? So for a bar magnet, the field around it is of the order of 10 to the power minus 2 Tesla. The Earth's magnetic field, the Earth's magnetic field is of the order of 10 to the power minus 4 Tesla. So Earth's magnetic field is in Gauss. That's where the unit comes from. It's measured usually in Gausses, but you can also measure in 10 to the power minus 4. That's the order of Teslas. So bar magnet is 100 times stronger than the Earth's magnetic field. You can see the powers. If you look at an MRI machine, you might have seen in some hospitals or diagnostic centers, that magnetic field, so for an MRI machine or for a CT scan which you use, those are, typically 1 to 3 Teslas. 1 to 3 Teslas. And the magnetic field is so strong that they tell you, please don't wear chains or metallic ornaments, carry mobile phones, don't do that. Remove your belt, everything which is metallic. In fact, if you have some piercings or maybe there is a rod inside of you which is made of some magnetic material, they do not allow you to keep that anywhere near that MRI machine. Because if you wear a chain, the magnetic field is so strong it will slit your throat. If you wear a bangle or something which is metallic, it will just cut your hand and come out of it. If you're on a chair which is metallic, the chair will be pulled inside the MRI machine. That's how strong a Tesla of magnetic field is. Got it? Isn't it crazy? Some of you are saying Final Destination. Yes, it is like Final Destination 5, 6, 7, whatever you want to say. Is that clear? I'm so thankful, Aniruddha. Please keep watching like this only and maintain that consistency, because I'm dedicating my entire teachings on the English channel just for you. Okay? Right? Perfecto. So now you got what a Tesla is, what the unit is, and what magnetic field is all about. One peculiar property of the magnetic field, which is not similar to that of electric field, is that the magnetic field lines never start and end, rather they continue and come back to complete the loop. So the magnetic field lines, you will always see, they form closed loops. Always the magnetic field lines, the magnetic field lines, the field lines, the field lines are always in a loop. There is no start, there is no end to it. Electric field starts from positive, ends at a negative. There is nothing like that for a magnetic field. Is that okay till this point? All these are very important characteristics of magnetic field. Now let's talk about how do we calculate this magnetic field using our Biot-Savart law. So what does it say? It says that, okay, fair enough. See, boss, you have a wire. Let's say you have a wire like this, maybe, carrying some current. It is going like this. You have a wire which is carrying some current. This is some wire. You want to find, due to this wire, how much magnetic field is there at a location. Okay, so maybe here, maybe there, maybe anywhere, doesn't matter. So let's say, for example, I want to figure out what is the magnetic field at, let's say, this particular point over here. Now, they thought this magnetic field will be because of all the parts of the wire. Like if I take this part of the wire, it will have some contribution. This part will also contribute. Every part of that wire some small amounts of the field. So they said, why not find out the contribution due to any one part, and then we can add the contributions. When you say add the contributions of things, summation, what comes to your mind? What comes to your mind? Obviously integration, isn't it? Hi Rama, nice to see you. All right. Yep. Integration. So that's what comes into picture if you want to find the entire contribution due to the wire. So we start off by taking an element of the wire. Let's say maybe over here or here, doesn't really matter. Okay. Some element of the wire, some element of the wire, some element of the wire, some again say element of the wire like this. Every small element out here, every small element out here will give some small magnetic field at every single location, like this over here and this over here and then this over here, this over here and then this over here. Every will give magnetic field at this point. So if I tell that the magnetic field due to an element due to an element, I will call it dl bar. Now what is a dl bar? Each of them is nothing but a dl bar. Dl means a small length of that current carrying element. So the magnetic field due to that element dl is, let's say, dB bar. Therefore, the net field due to the wire, it could be in 2D, 3D, it could be curved, straight, anything, doesn't really matter. That net field will be integration of those small vectors. Integration of those small dB vectors. That is how I will get it. Is this absolutely clear, my dear warriors? Is this absolutely clear? Give me a thumbs up and smash the like button in case you have forgotten that. Okay. So you have to integrate the field due to contribution due to every single element of that wire. But sir, how much is this dB, sir? How do I calculate the integration if I do not know dB? Okay. So let's think, how do we calculate the dB? So we take a small element. I will call that element dl. That dl element is remember, it's a part of a big wire. I'm not showing it, but we all know it is there. And there is some current which is going in it. And the current which is going in it is basically I. So I is the current which is going in it. dl is the small element. I want to figure out what is the magnetic field at this point. So what I do is I draw a positional vector of this point, positional vector of this point respect to the element. So that positional vector or position vector is r bar. So what is r bar? I'm mentioning it clearly. It is the position vector of the point where the field dB bar has to be found with respect to the element dl. With respect to the element dl. So with respect to this element, I want to figure out the magnetic field over here. First of all, let me tell you the direction of it. Then we will go to the magnitude. The direction of dB is very simple. All you need to do is take the dl vector, take the r vector, and then cross product it. So dl is here, r is here. Use your right hand, align the four fingers in the direction of dl, slowly curl it towards the r. Your thumb will point towards the dB vector. So as you can see over here, the dB vector will be towards me. dB vector will be towards me. Everybody fine till this point? Yeah, perfecto. Yes, what do you want, Bhanu? Please let me know. Oh, yeah, the physics planner, definitely it's coming tomorrow. Okay, because the entire plan is to be made, right? So it starts from August 1st to end. Okay, so the direction is given by the direction of dB bar is given by your right hand thumb rule. Right hand thumb rule. All you need to do is do dl vector cross product it with the r vector. That will give me the answer of the dB bar. Okay, direction is also done, sir. So what about the magnitude? That is the only thing remaining. So the magnitude according to the Biot-Savart law is found out to be proportional to some things, and you convert it into equality, so that equality comes out as the dB is equal to dB bar is equal to, there is mu naught by 4 pi, which is a constant of proportionality. We'll come to what mu naught and everything is. Okay, mu naught by 4 pi. And then you have I dl cross product with your r vector, and the whole thing divided by r cube. This is the formula of the magnetic field. This is the formula of the magnetic field due to that element. Now we'll understand everything one by one, don't worry. So let me first block this off. What is this mu naught? Okay. First of all, mu naught is called as the permeability. Permeability of vacuum. Permeability of vacuum. Remember permittivity? Permittivity is to tell me how much is the electric field permitted inside a medium. It was a measure of that. And permittivity of vacuum was 8.85, 10 to the power negative 12. So permeability tells me, how much is magnetic field permeable. Permeable is a property of entering into something. Like the rocks are permeable. That means if rain falls, the rocks will allow the water to seep in. They are permeable. If they are non-permeable, means the water will not enter in the rocks. The rocks are hard. If there are a lot of cracks, lot of porous nature is there of the rocks are permeable in nature. It's sponge-like. So same way, permeability is how porous is that medium. It's a measure of that. Now, that factor always is compared with vacuum. Vacuum is your standard, and based on that, other mediums are compared, and then you have relative permeability and other things, which we'll talk later on. For now, let's deal with vacuum and air, and the permeability of vacuum or free space or roughly air is 4 pi into 10 to the power minus 7. That is the permeability number, 4 pi 10 to the power minus 7. Keep this in mind. So if you ask me what is this number, mu naught by 4 pi, 4 pi cancels, it will be 10 to the power minus 7 is the SI constant. Is that absolutely clear, my dear warriors? I dl cross r. Do you see the cross product over here? Dl cross r. That is giving me the direction. If I don't want the direction, the magnitude part, well, that is straightforward then. This will be nothing but dB in terms of magnitude will be mu naught by 4 pi. Then we will have directly I dl sine theta, I dl sine theta into r, but that r will cancel by r cube and we'll be left with r square. What is theta? Theta is basically the angle made between them, how much ever that angle is. So ideal sine theta r, but that r will cancel with r cube. So that's why r square is left. Is this clear? So this is the magnitude, this is the direction. Better to remember this because this gives you the complete picture. Okay, fair enough, everyone? Great. So think and tell me now, using Biot-Savart's law, if I have a wire carrying element like this over here, This is some current I, this is some element. Tell me at the following locations, what is the direction of the magnetic field? I will give you 3-4 points. You need to tell me the direction of the magnetic field at every single point. Point number 1, point number 2, point number 3, and point number 4. Come on. Point 1, point 2, point 3, point 4. They are all in 4 different directions with respect to the element. Think carefully. Well, starting off with the first point over here. If you go over there, think carefully. DL will be there. R vector will be on the top, positional vector. So if you do DL vector cross R vector, the thumb is coming towards you. So the magnetic field will definitely be towards you. So it should be like a dot over here. It should be like a dot over here. Is that right? So the magnetic field number 1 will be towards you. What about the second point? What about second point? Come on. Yeah, towards us. Perfect. Many of you got it. Second point. Many people will make a mistake over here, but be careful. The positional vector is like this. The moment you take a cross product, guys, the angle between them is 0. Sine 0 is a 0. And even if you take two parallel vectors to be crossed, the answer is a 0. So there will be no magnetic field at all. So the magnetic field at 2 will be 0. Not just 2, even 4, guys. I mean, just look at it. This is the positional vector. This is 180 degrees. Sine of 180, 0. So answer is a big fat 0. So the magnetic field at number 4 is also 0. So in fact, whenever you have a wire, along the axis, the field is 0. So if I take a wire like this, anywhere on that line, this side or this side, due to this, there will be no contribution because the cross product will be 0. So on the axis, the field is 0. So on the axis of the wire, the field is 0. That is a star result which I am getting. What about this particular point over here? Well, DL is there. My positional vector is here. DL, my right hand 4 fingers go that way. Slowly move towards down. I can see my thumb going inside the plane of the board. So obviously the magnetic field will be inside at number 3. It will be inside. This is outside. Everyone clear? Got it? No, not all are towards us. Some are towards us. Some are away from you. Some are not there only. All right. If you are not finding certain modules very good or they are very tough, if you want to go from the basics, see, one is HC Verma. HC Verma problems are really good, but they are standard problems. They won't go after a point, you won't get too much variety and not up to the mark after a point. Standard problems are really good. So then you will have to go to DC Pandey, and or you can also go to Cengage at times, but Cengage is little bit unstructured. For physics, I would say DC Pandey is slightly better. And then you can go to the previous year books for additional practice. But sir, can you give me one book which has everything? Then I would say use the Tattva module. So the Tattva module looks like this. There are 4 levels of exercises. Students 100% get confidence in level 1, and then you go to level 2, then you go to level 3, and level 4 it also comes with theory. So this is good enough book, and it has PYQs of mains and advanced and all kinds of questions. So that is a good book which you can use, the Vedantu Tattva material. The link for buying it is there in the description box, so you can use it. It will be couriered within 2 to 3 weeks. Okay, cool. Right. So let's solve a question which came here. An element delta x is the length, I cap means the direction, is at the origin. It carries some huge current, 10 amperes. Magnetic field on the y-axis at 0.5 meters is how much? That is the question. Okay. Yes, you can use the last year series or even this year series, but this year series I would advise you because new problems, new pattern, more detailed. Yeah. So it's completely up to you whether you want marathons or whether you marathon one shot or you want small classes. But again, distributed. It's completely up to you. But live is always better. That habit of consistency will build up. So this is R, this is that element. So I want to find the magnetic field. Let me use our magnitude formula. Magnitude formula is mu naught by 4 pi I dl divided by R square, and here we have sine theta. So what is mu naught by 4 pi? It is 10 to the power minus 7. What is the current? It is given to be 10 amperes. What is the length? The small length, I think, is delta x. Now, is that delta x given to me? Delta x I cap, okay, from the element delta x of 1 centimeter length. Yes, it is given to be 1 centimeter length. So delta x is 1 centimeter. 1 centimeter is 10 to the power minus 2 meters. Is that right? 10 to the power minus 2 meters. Okay, perfect. Into sine theta. Well, the angle between them is 90 degree, and we all know sine of 90 degrees is 1. So I'll just put the number 1 over here. The whole thing divided by r square. R is the distance. So distance is 0.5 meters. So I just have to put 0.5 square over here. Is that right? Okay. So what do we have? 10 to the power minus 1, and this will become 10 to the power negative 8, and we have 0.5 square, which is 0.25. 1 by 0.25 is 4. So 4 into 10 to the power minus 8 Tesla. So 4 into 10 to the power minus 8 Tesla, which is C option. That is the correct answer. So direct application of Biot-Savart's law has come. Cool? All right. Okay, great, great. Every lecture is a small part of the big unit or the chapter. So, we are slowly progressing, right? All right. So just follow this. Everything will be completed on time so that you will also complete the revision aspect. Now, let us move to the next part where we apply it for two things today. Only two things, but good collection of problems will come. Okay. First is a wire. Second is a coil with arc on the axis, everything. So let's talk about a straight wire. Magnetic field due to a straight wire. So imagine like this. We have a wire which carries maybe current like this. Okay. The wire is carrying current like this. Then the magnetic field will be around it in this particular manner. Like this. Like this. Okay. So it will be concentric circles like this. If you reverse the direction of the current, if you reverse the direction of the current, the magnetic field will also reverse its direction. So then it will be like this. Slightly difficult to draw these circles in 3D, but I'm trying my best. Okay. That is how it looks like. Basically, we are using the right hand thumb rule. So if you think about it carefully, you will realize that if I'm holding the wire such that the thumb of my right hand, points in the direction of the current, then the curled fingers, point in the direction of the magnetic field. You will notice that very easily. Is that right? Then the curled fingers point in the direction of the magnetic field of the right hand. So this is how it works like that. So the thumb should point in the direction of the current of your right hand, and then the curled fingers, then the curled fingers, they will give you the direction of the magnetic field. They will give you the direction of the magnetic field. Is this diagram clear? Nice hand I have drawn. Very good. Okay. Optics after magnetism, like EMI and everything, we are going to go to optics only. So this month is dedicated completely for magnetism. So towards the month end, maybe we'll be starting off with all kinds of optics, ray wave optics, right? Waves, everything. Okay. So now having said this, let's say my wire was in fact like this. Okay, just imagine my wire is carrying current like this, or let's say it is carrying current like this, or let's say the wire is coming towards me only, or let's say the wire is going away from me. Then how will the magnetic field lines look like? All the four situations I'm making you visualize, because I just went up and down, we saw it. As you can see in this particular scenario, if you are on the right hand side of this wire, the magnetic field lines are going inside the plane of the board. And if you're on the left hand side, then the magnetic field is coming towards you. It is going like this, going inside, going like this, coming towards you. Whereas for this, it is coming towards you on the right side, right? If you hold the thumb down like this, the fingers on your right side are coming towards you. But on the left side, they are going inside. They are on, they're coming towards you. That means it should be like this, my bad. Yeah. And on the left side, they are going inside. So that is why the cross. So I hope it is clear. It is coming like this and going inside. Here it was coming like this and going like this. Same way, let's think over here. If the current is going this way, hold your thumb like this. Imagine you're holding a current carrying wire. So as you can see from the top, it will come towards you, and below it will go away from you. So if you are anywhere here, it will be towards you. If you are anywhere here, it will be away from you. Is this clear? Just picturize you're holding a wire. If you just do like this, it might not be clear. So hold a wire, then on the top it is towards you, and below it is away from you. Same way over here, picturize you're holding the wire like this. If you curl your fingers, then on the top it is going away from you, and below it is coming towards you. So below it is coming towards you, and on the top it is going away from you. Clear? Perfect. What if this? Imagine the wire is coming towards you. So imagine this is the wire, the pen, and I'm holding my thumb in that direction. So the fingers will go like this. That means the magnetic field will be in this direction. So it is in the anti-clockwise direction, as you can see, anti-clockwise direction. Okay, it is in the anti-clockwise direction. Here, it is obvious that it will be clockwise, but still, just think about it. If my thumb points inside, then my curled fingers go clockwise. So the magnetic field is in the clockwise direction. If this is clear, then we can go ahead. Is the directional aspect clear for a straight wire carrying current? Do we use left hand thumb rule? See, there are left hand thumb rules, yes, in Lorentz force and all of that, but we will not use left hand thumb rules, right hand thumb rules, etc. separately. We will just stick to cross products everywhere, because in the exam you will only forget in the left hand, was this force, current, length, was this right hand, which one was what? See, that is okay till 10th standard. The 10th standard kids, they become very happy using left hand rules or right hand rule, and they keep acting mental in the classroom. But you guys are grown ups now, so you have to use cross product every single time consistently, or else that confusion will be there in your head when to use which finger for what. Okay, so let's not get there. Let's consistently use right hand rule, thumb and four fingers curled. That's all you have to keep in mind. Is that okay? Perfecto, right? 11th is also missed. So Himang, I will make a separate timetable just tomorrow, and I'm making a planner for all of you. It takes time. It's not like I just can do something and come up over here. I'll come up with a plan tomorrow, okay? For you guys to crack JEE 2026 in the remaining months. Right. Sir, the direction aspect is very clear, sir, whether the wires are up, down, left, right, towards me, away from you. But what is the magnitude of that current? Oh, sorry, what is the magnitude of that magnetic field? Now, we are going to talk about basically, we'll come to this later on, okay? Straight wires, finite straight wires, finitely long straight wires. See, if my wire is infinitely long, if my wire is, let's say, infinitely long, we will get a special formula, and we can do it using Ampere's law, which we are going to discuss next time. But for now, see, These are the kind of wires. One is infinitely long wire. One is infinitely long wire. One is semi-infinite wire. One is semi-infinitely long wire. Looks something like this. And another one is a finite wire. Another one is a finite wire carrying current. These are the three different wires which you need to study. This, and this, all three depend on this guy's formula. If you know for a finite wire, you can also find for semi-infinite and also for an infinite wire. So this is your finite wire. This is finite. This is semi-infinite. This is just infinitely long wire. It's a very long wire, basically, like say imagine 10-20 meters long. So that end and this end very far away. Okay. This is semi-infinite means you are standing somewhere over here. You are just standing somewhere over here. In the infinite case, you are just standing here, okay, in front of it like this, just in front. Semi-infinite means one side there is nothing, other side it is infinitely long. Like the wire starts only here in front of you and it is going like this long, 10-20 meters long it is. But down there is nothing, only on one side there is infinity. Finite means you are standing here and you can clearly see the endpoints. Okay, one point is here, other point is here. These are the ends of the two wires. So it's a finitely long wire. Got it? So these are the three different wires which we have to study. If you know finite, you can do semi-finite and also completely infinite wire. Let's see for finite what is the formula and how it has been derived. So if you take a wire which is finitely long, and let's say the current through it is basically I, and I am standing at some distance from that particular wire. It could be anywhere. Okay. And that distance is, let's say, R, X, D, whatever you want to call it. Okay. Some people also call it D. It's perfectly fine. And here I want to figure out what is the magnetic field. First of all, direction is very obvious because the current is going up. The magnetic field lines will go inside on right side, and from the left side it will be towards me. So 100% it is inside. So the magnetic field will be like this. This will be the magnetic field. But how much is that particular magnetic field is the question. For that, I need additionally two more data points. And those data points are nothing but you take that point and the end point. You take that point and the end point, join it geometrically and mark the angles. Let's say this particular angle, I call it alpha. Let's say this particular angle, I call it beta. So what is alpha and beta? Those are the angles subtended by the ends of the wire with the perpendicular drawn. So let me show all the things which have been marked. D is nothing but the distance from the wire. D is nothing but the distance from the wire. Distance from the wire. Then you have, of course, alpha and beta are the angles subtended by the ends. Angles subtended by the ends of the wire on the perpendicular distance. On the perpendicular distance. Okay. I is the current, that is standard. Now, can you think what we should do next? Can you think what you should do next? Yeah, of course. We have to take multiple segments to integrate and figure out the next complete magnetic field, which is what I told you at the beginning of the class here. If there is a long wire, you want to find the net contribution. You take the magnetic field due to every small contribution of that element and you add them up, basically integrate them. So that's exactly what we'll have to do. So we have to take a generic point and basically integrate. So that's the procedure. So I'll just give you a brief about it, how that procedure goes. So it all starts by taking some random generic point over here and some generic element over here again. So that generic element, I can call it as dy, and it is at a distance of y from the origin. This is your x-axis, this is y-axis. That dy element, that element dy is carrying that current. Okay, so that element dy which is there, it is carrying that current. I'll just mark this element, and that is also making some angle over here. Let's say I call it theta. It is making some angle theta over here with the positional vector. Do you see, this is basically the positional vector? This over here is the positional vector with respect to the element where you want to find the field. So that is basically your R, and the magnetic field will no longer be B, it will just be dB. It will just be dB due to this small element. I hope this is clear. So by logic, my dB will be mu naught divided by 4 pi. Then I will also have I dl. dl over here is dy. And then I will also have sine theta. And the whole thing divided by r square. And the whole thing divided by r square. Now, r can be written down geometrically in terms of d and theta. Okay, you can write it in terms of geometry. How? Observe carefully. This particular angle over here is pi minus theta. This is hypotenuse, this is perpendicular. So in this triangle, you can take sine of pi minus theta. Sine of pi minus theta will be opposite side divided by the hypotenuse. What is sine of 180 minus theta? All silver teacups, it's in the second quadrant. Sine is positive, and sine of pi minus theta is just sine of theta. So sine theta is nothing but d by r. So we got one thing over here. Sine theta is d by r. If you want, you can put sine theta as d by r here, or you can put r in terms of sine theta, whichever you want. That is the just a substitution. Next is converting dy, because I can't integrate dy. I have to convert dy into d theta and all of that. So write y in terms of theta. How do I write that? Observe carefully. Cos theta if I write. So cos of theta is adjacent side, which is y, divided by the hypotenuse, which is basically r. Which is basically r. Is that right? That is one way of writing. Or we can also write tan of pi minus theta. Tan of pi minus theta. Opposite side by adjacent side. So opposite side is d. Adjacent side is basically nothing but y. What is tan of pi minus theta, my dear warriors? Yeah, think about it. What is tan of pi minus theta? It will be tan theta, but with plus or minus sign. Second quadrant we are talking about. Second quadrant tan is negative. So this will be nothing but minus of tan theta is nothing but d by y. So from this you will get y is equal to minus d into 1 by tan theta, which is nothing but cot of theta. Everybody with me? Yes, very good, very good, very good, very good, very good. What next, guys? Think about it. What next? What is the next step? We want dy, right? Yes, we want dy, right? What do we do for dy? Take derivative. So if I take dy by d theta, it will be minus d derivative of cot theta with respect to d theta. What is the derivative of cot theta? What is the derivative of cot theta? Quickly, come on, my dear warriors. Quickly, my dear warriors. Yes, it is cosec square theta with a negative sign, yes or no? Cosec square theta, yes or no? Come on, guys. So dy by d theta will be minus of cosec square theta. I hope this is clear. Yes, very good. So minus minus cancels. What do I get my dy as? Minus minus cancels. It will become cosec square theta d theta. So what happens when you substitute dy? When you write r also in terms of theta, it will become a trigonometric integration. Are you seeing that already? If I substitute over here dy as cosec square theta d theta, r I can write it as, over here only you can see, r is nothing but d by sine theta, which is basically again a trigonometric identity, right? Which is nothing but d cosec theta, which is nothing but d cosec theta over here. So if you substitute everything over here, it's a pure trigonometric identity, trigonometric function, sorry. So you can just solve it using trigonometric integration with proper limits. So the magnetic field will be integral of dB. So lot of things like mu naught by 4 pi, and even that current is going to just come outside, and you will just have integration of dy, and then you will have sine theta, and you will have r square over here. You can substitute everything right into this. Dy is basically cosec square theta d theta. R is nothing but d cosec theta and all of that. So solving this, you will get the final answer. Got it? You understood the method now. That is important, that is needed. Okay. Now the exact procedure is over here. After this, you will be able to do it. So what is the answer, sir, that we will get? Okay. So the answer that you get is as follows. The net magnetic field that you get is mu naught by 4 pi. Mu naught by 4 pi. You will have over here the value of the current. You will have over here the value of the current divided by the distance, and finally over here you will have sine alpha plus sine beta after you put the limits of the integration. Okay, after you put the limits of the integration. So this is the final form that you get. Mu naught by 4 pi I by d sine alpha plus sine beta. That's it. Okay. The session will go on for 1.5 hours, so around till 10 o'clock, not more than that. Oh, nice, sir. So, how can we use this for semi-infinite and infinite wires? Let's have a look quickly. Okay, for finite wires, I just gave you the formula. Okay, let me get rid of this now for a moment. So, can you guys quickly think for semi-infinite, what is alpha and what is beta? Okay, let me start thinking. The first end of the fire is infinitely far away. The second end is over here only. So can you quickly guess and tell me what is alpha? Alpha is this entire thing with the perpendicular, which is nothing but 90 degrees. Can you see that? Alpha is basically this entire thing over here. So alpha will be 90 degrees, but the other end with the perpendicular makes nothing. So beta is 0 degree. Beta is basically 0 degree. So what will be the magnetic field at this particular point? The magnetic field will be mu naught by 4 pi I by the distance into sine of 90 plus sine of 0. Okay, sine 90 is 1, sine 0 is 0. So it will be nothing but mu naught I divided by 4 pi d. We got the answer. Perfect. How about the infinitely long wire? Well, this end is here, the other end is right over here. As we can clearly see, this is basically my alpha and this is basically my beta. Both alpha and beta both tend towards 90 degree. So think what should be the answer of the magnetic field over here. The magnetic field will be mu naught by 4 pi. I is there and d is also there. We have sine of 90 plus sine of 90. What is sine 90 plus sine 90? 1 plus 1 is 2. So it will become mu naught I divided by 2 pi d. That 4 became 2 because sine 90 and sine 90, 1 plus 1 is 2. 2 and 4 cancels to become 2. Cool? Perfect. That's the answer. Yeah, you can also think I can multiply this by 2 because if this half is this much, the other half will also contribute the same thing. So 2 times of this, again, it will cancel out. But I just wanted you to see the application of the formula. That's why I have done it that way. Yeah, you can also multiply it by 2. That's perfectly fine. Okay, sir. Perfect. I got it. So the derivation goes, just by integration of all these things. All right. So now, having said this, let's do a quick question over here. Let's do a quick question over here. And many of you might be really thinking, how the hell do we do this? It's a very tricky question. Okay, let's see how many of you can actually do this. Hmm. This is at a distance of maybe 30 centimeters. This is, let's say, 40 centimeters. And let's say there is a current of 2, or let's say 10 amperes which is going, and it goes on till infinity. The wire starts over here. This is one end of the wire. So you are not, don't say this is infinitely long. No, this is a semi-infinite wire. You can think of it like that. Okay, this is a semi-infinite wire. But you are not in front of the other end. You are off the other end. That is the crazy part. Are you able to visualize this? This is going till infinity, but you are not in front of the other end. You are somewhere off track. It's a very cool question. Yeah. So how do we do this question? Okay. How do I figure out what is the magnetic field over here? The current is going like this. So the magnetic field will be definitely inwards by right hand thumb rule. I want to figure out the magnetic field. Okay. So here is what I will think. I have to join the ends from the point where I have to find the field. One end is infinitely far away. The other end is right over here. Okay. So tell me quickly what is alpha and what is beta over here, because after that it is just formula substitution. I have to just use mu naught by 4 pi. I have to put current divided by distance, and I have to do sine alpha plus sine beta because it is a finitely long wire. Mu naught by 4 pi is 10 to the power minus 7. Current is 10 amperes. That is also clear. What is the distance I need to figure out, and other things which I'm going to put over here. Let's see. Distance. This is the wire. This is the perpendicular distance. This is basically D. So technically this is D. 30 centimeters means 0.3 meters. So I'm just going to put the number 0.3 over here. I hope that is perfectly fine. Yeah. What about the other numbers like alpha and beta? Quickly answer in the chat box. What should be alpha? What should be beta? Alpha is the first end. So the first end is here. With the perpendicular drawn, well, you are making 90 degrees. Can you see? This is basically 90 degrees. So alpha is definitely 90 degrees. So sine of 90 is definitely 1. So 1 is coming over there. What about the next number, beta? Well, think carefully. With the other end, with the perpendicular, this angle is basically beta. So I think this is a familiar triangle to me. 30, 40, this will be 50, 3, 4, 5. Yeah, 3, 4, 5 is a familiar triangle. This will be obviously 50 centimeters. Do you see the number 5 and 3 together? Whenever the numbers 5 and 3 are together in a 3, 4, 5 triangle, 30, 40, 50 triangle, the one angle closer to 5 and 3 or 50 and 30 will be 53 degrees. So this is technically 53 degrees. So shouldn't beta be 53 degrees? Yes or no? Think about it. Shouldn't beta be 53 degrees? But that is the catch. Beta is not 53. Can you guess why? Because when I gave you the formula over here, where is it? When beta is on the other side of alpha, that's how you measure the angle beta. Like alpha is on one side, beta is on the other side. But imagine this point is over here, then beta will be on this side, it will be negative. So the assumed positive direction of beta is when it is on the other side of alpha. But if it is on the same side, well, then it's going to be negative, guys. So technically, it is minus 53. Because if this point was here, then this will be plus 53. Obviously, the other side has to be negative 53. So that is the biggest catch in this problem. Got it? Everyone? Perfect. So what is sine beta? Sine 53. Sine of 53, guys. Come on, think about it and tell me. Sine 53, 4 by 5. But this will be now minus 4 by 5. Many students put it as plus 4 by 5. Yeah, that is a common mistake. That's why I did this problem with all of you. Now we can do and proceed this with this question. This will be 10 to the power minus 6 if you want. 0.3 is 3 by 10. 10 goes on the top. 1 minus 4 by 5 is just 1 by 5, of course. So this will become 10 to the power minus 5 and this will become 1 by 15. So that's it. This is the answer, 1 by 15 into 10 to the power minus 5. If you want, you can convert it into decimals. That's not a big deal. So 10 to the power minus 5 by 15 Tesla is the answer for this question. Got it, everyone? Okay. I'm so glad, Prajit, you love the lectures, and I'm hoping that you continue your journey of your JEE learning, and all the best, and continue watching the lectures over here. I'm pretty sure you will crack it. Let's go to some questions which are over here. This was asked previously. I'm pretty sure you will be able to do it. Two long straight wires carry equal currents in the opposite directions as shown. The separation between them is this much centimeter. The field at the point midway between the wires. Okay, let's think. One line going like this, one line going like this, midway. So if I talk about this wire, then at this point, if I hold the thumb like this, the fingers go inside, the magnetic field is inwards. Magnetic field is inwards. Due to this wire, if I hold my thumb like this, then my fingers of right hand again go inside. So again, due to this wire, the magnetic field is again like this. But since this is the midpoint, whatever contribution this will give, same contribution this will give, both of them will add to give you the net field. So the net magnetic field is the magnetic field due to the wire which is carrying current like this, plus the magnetic field due to the current which is carrying current like this. If I add both of them, I'll get the same answer. But since both of them are equal in magnitude, I can definitely say this is 2 times of magnetic field due to this wire, or I can also say it is 2 times, I can also say it is 2 times the magnetic field due to this wire. How am I able to say this? Because of symmetry. Because of symmetry. Same distance, same current. Even if the distance or currents were different, I could not say this. Yeah. Perfect. Amazing. Great. Absolutely, absolutely clear. Very cool. Awesome. Now, how much is this? Well, it's an infinitely long wire. Two long straight wires are there. And we just discussed that particular thing. Where did we discuss? Due to infinitely long wire, mu naught I by 2 pi d. Mu naught I by 2 pi d is the formula. Okay, so we just have to put over here. We just have to put over here mu naught I divided by 2 pi d. So what do I do over here? Think carefully. 2 times mu naught is nothing but 4 pi into 10 to the power minus 7. This whole thing divided by 2 pi. Current is also there. How much is the current? I think 10 amperes. Okay, we'll put 10 over here. What's the distance? Think carefully. Now it is mentioned to me that the distance of separation between them is 5 centimeters. So any one distance, like for example, this one will be 2.5 centimeters, which is 2.5 into 10 to the power negative 2 meters. So I will just put that 2.5 into 10 to the power minus 2. That's it. So we have it over there. So what will happen, guys? 4 pi and 2 pi will cancel. It will become 2. 2 into 2 is basically 4. Yeah. So that will become 4. Just check this out. 2 pi and 4 pi cancelled. 2 is remaining. 2 into 2 is 4. This 2.5 will be as it is over here. Now 10 raised to minus 2 on the top will become plus 2. Plus 2 and plus 1 will become plus 3. Minus 7 and plus 3 will become minus 4. So it will become into 10 to the power minus 4. So if you want, you can just write this slightly better. 4 40 by 25 into 10 to the power minus 4. Yeah. Or you can also write this as 400 by 25 into 10 to the power minus 5. Now it becomes very clear. How is it divisible? Yes. Come on, guys. How many times? 25 times are 250. Yeah. So come on. Now you should be able to do this. Now you should be able to do this. Yes. How many times? 16 times, 17 times, 18 times, 13 times. Come on, my dear warriors. How many times? Yes. Perfect. 16 into 10 to the power minus 5. So they have answered it in micro Tesla. So this will be 160 into 10 to the power minus 6 Tesla. So this will be 160 micro Tesla, which is option A. Which is option A. Got it? Perfecto. Amazing. Amazing. That's how you solve these questions. Okay. So that's how you solve these questions. 160 micro Tesla. Now, very similar question. I am pretty sure you will be able to solve this. The only difference, the currents are different values, distances are same, but the direction of the current is same. Will you be able to do this as homework now? Easily you can do this. Homework. I will give you the quick hint over here. I want all your answers in the comments. Answer should be there in the comment section. Think carefully. This current is going up. If you hold your thumb like this, the field will go inside. So due to this guy, the field is here. Whereas due to this guy, again, if you hold the thumb like this, the fingers come towards you. So the field will be towards you. So they will not add in magnitude, they will subtract in magnitude. That is your biggest hint. Is that clear? Yeah, everyone, they will subtract in magnitude. Yep. I think we have a lot of 9th and 10th standard students. I feel that we should start a 10th standard, 9th standard foundation English class, which will be, I think, the first in the country. And although there are a lot of 9th and 10th channels, but they do board level stuff only. We should do board CBSE in English, I think, right? CBSE English, I don't think it is there anywhere. Is there any channel? Do you want such a channel? And maybe the foundation aspect for JEE NEET, which teaches you beyond your boards with the best teachers for JEE and NEET. That would be something to look forward to. You let me know, guys. Maybe we should. Yes. Okay. So try this question out. Answer should be there in the comments, and you will get the PDF after some time. So it will be there. The solution, the answer key, everything will be there. Okay. And just going ahead now. Okay. What is the magnetic field at the center of polygon? We go to a polygon. We saw a straight wire. See, you take any polygon, maybe a triangle, maybe a square, or maybe some n-sided polygon. You have to know this. Doesn't matter. Okay. You take any polygon and you want to find the magnetic field at the center. I'll tell you what. You take any one side and find the magnetic field due to that side. For example, I take this side, or let's say this side, or let's say this side, or let's say this side, and join the ends of those sides with the point. Join the ends of that particular side with the point where you want to find the field. Also drop the perpendicular. Also drop the perpendicular distance. This is your perpendicular distance. I think now you can clearly see that there is one alpha over here, there is one beta here. There is one alpha over here, there is one beta over here. Can you see that? There is one alpha over here and there is also one beta over here. There will be beta and there will be alpha. There will be beta, there will be alpha. There will be beta and alpha. They will both be equal. So you find the magnetic field due to one side using our formula mu naught by 4 pi current divided by that distance which is there. Okay, and use your sine alpha plus sine beta and all of that. Sine alpha plus sine beta. Whatever number of sides are there, you multiply it with that. Multiplied by n, which is the number of sides. You will get the net magnetic field. You will get the net magnetic field at the center. Isn't it clear? Isn't it obvious? No? You find out due to one guy, every side will contribute the same amount and all of them will keep adding and you will get the net magnetic field. Got it, everyone? Yeah? Awesome. So I think we should do that. Right. So this is one thing, but there is also one more addition to this, and I want you to pay attention to that. Say, for example, you have any polygon like this, regular polygons only. Okay, doesn't matter. Imagine the current enters like this and leaves like this, or the current enters like this and leaves like this, or let's say the current enters like this and leaves from here. Now I ask you, what is the magnetic field at the center? What is the magnetic field at the center? Everybody will be like, sir, now what to do? Now we can't do that because some of them will add, some of them will subtract. See, in the previous diagram, what used to happen, if this side, the magnetic field is this way, this side will also give the same way, this side will also give the same way, this side will also give the magnetic field in the same way. All of them will add the fields to give you the net field. That is why we were adding, that means you are multiplying with the number of sides to get the total magnetic field. But the problem with these questions, when the current enters like this, imagine what will happen. The current will get distributed somewhat here, like this. And again, it will collect. Here also, the current will get distributed into two branches. Here also, the current will go like this and like this. So now what to do, sir? Now what to do? It will subtract, no? So something will cancel. But sir, these sides are more, this side is less here. Sir, here two sides are there, here two sides are equal. So maybe here it will be 0. Here there is one side, here there are two sides. Maybe it will not cancel out completely. Here one part of the current is going here. Here three sides are there. So maybe again it will not cancel. That's what you are thinking. But that is not the case. What happens? Even if there are more sides here, 3 versus one side, the length of this wire is more, so the resistance is more, so the current is less. So we are now talking about a balance or a compromise between the current versus the number of sides. Whenever the sides are more, the length is more, resistance is more, current is proportionately less. So it balances out the effect. Yeah, it balances out the effect. So the magnetic field due to these three sides versus this one side will cancel out each other in every single case. So in all the cases, in all the cases, you will see that the magnetic field at the center is 0. The magnetic field at the center is going to be 0. No matter whichever polygon you take, doesn't really matter. Okay, you take any, even 100 sides, 200 sides, you can make it a circle also. Circle is an infinitely sided polygon, by the way. Yeah, you can take circle, hexagon, whatever. If current enters once inside, and it can leave from any place, really doesn't matter, it can leave out from here also, you will see the currents will always inversely, I don't know what just happened, you will always see that the currents will inversely distribute themselves, to the number of sides, so they will kind of compensate each other, and the net field at the center will always be 0 in such situations. Cool. Simple trick. Many times in the exam they have asked these diagrams. People wasted their times calculating it, only to find out the answer is 0. Only if you would have listened to this class, that you would not miss out on that simple trick. The only thing in these questions is that the current is going in the same direction. So the fields will also add up. The fields will ah, the fields will add up. The fields will add up to give you the net field. So let's do a question on this. We have a question already. There you go. So as shown in the diagram, a current of 2 amperes is flowing in an equilateral triangle. The magnetic field at the center of the triangle is. The magnetic field at the center of the triangle is. So let's start by doing a small derivation right over here. So this is our triangle, and basically this is the point, and this is the distance, and basically this is the side length. This is basically the side length. Everybody fine till this point? Yeah, okay. Now let's say the length of the side is A. So if at all I would have drawn the altitude, and since this is an equilateral triangle, the altitude the altitude will be how much in length? Can you guys guess how much will be the altitude, guys? Because obviously this angle will be 60 degrees, right? This angle will be 60 degrees. This is the hypotenuse. This is 90 degrees, of course. So it will be nothing but hypotenuse times of sine 60, which is a root 3 divided by 2. That is the length of the altitude. But I wouldn't need that. I just want this distance for my calculation. So how do I calculate that particular distance? Come on, guys. What if the current will flow in 3 ways? How will it flow in 3 ways? Can you explain it to me? Because if it will go in, it has to come out, right? If it goes in, it has to come out. So think about it. If there are 3, it goes in and goes out. Doesn't make sense. If it goes in, it has to come out. So it has to be even numbers. And when we are talking about polygons, either there is an entry point and there is an exit point. How can we have 2 entries and 1 exit, or 1 entry and 2 exits? It doesn't make kind of, yeah, sense out there. I hope that is clear. Okay, fair enough. All right, all right. So now what? Next, what do we do? Think about it. Yeah, ratio of O and G. Yes, what is this point exactly? This is exactly the centroid. This is basically the centroid. So it divides it in the ratio of 1:2. Yeah. So come on, think and tell me, how much will D be equal to? How much will D be equal to? How much will D be equal to? Yes. Think and tell me, guys, quickly in the chat box. Right away, right now. Yeah. Right away, right now. Think carefully. How much will it be? Yes, guys. What shall it be? Think carefully. One of those students who thinks the Roar series is the GOAT. I'm so glad, Jatin, means a lot. And continue watching and keep watching live also over here. Yes. What shall it be? This will be in the ratio of 1:2, right? Everyone with me on this? Guys, am I visible? Let me know quickly in the chat box. Let me know quickly in the chat box. I was just explaining everything and I don't know when I lost the connection. Okay, do you remember that this is the centroid? So it will divide it in the ratio of 1:2. Yeah, 1:2. Okay, everything audible, visible? Okay. So this is closer, this is far away. So how much will this distance be? This will be, if it is in three parts, this is one, this is two. So this will be 1/3, right, into the altitude length, So it will be 1 by 3 of a root 3 by 2. Root 3 cancels. So it will be a and by 2 root 3. So that is what the distance will be. But is the distance also given to me? Side length is 4 root 3. Side length is 4 root 3. So side length is 4 root 3 by 2 root 3. Root 3 cancels. It will become 2 centimeter, which is 2 into 10 to the power negative 2 meters. So D we got. D we have got. All right, everyone. Perfect. So this is one part, this is two parts. So if you divide the altitude into three parts, this is 1/3 of the entire altitude. Okay, last thing over here which we need is joining these lines over here and figuring out how much the angles will be. This is basically one of the angles, which is alpha, and this is basically the other angle, which is beta over here. This is 30, this is also 30. So naturally, each of them will be 60, 60 each. So the magnetic field due to any one side will be mu naught by 4 pi I by d sine 60 plus sine 60 two times. Mu naught by 4 pi 10 to the power minus 7. Current value is of 2 amperes. So put 2. Distance, we just figured it out. It is 2 into 10 to the power minus 2. Whole thing sine 60 into 2 is 2 into root 3 by 2. Lot of 2's out there. 2 cancels, 2 cancels. Okay. We are just left with 10 to the power minus 7 by 10 to the power minus 2 multiplied by root 3, which is 10 to the power minus 5 multiplied by root 3. That is the field due to one side. So the net magnetic field will be 3 times the magnetic field because 3 sides are there. So 3 multiplied by root 3 multiplied by 10 to the power minus 5 Tesla. 3 root 3. 3 root 3 into 10 to the power minus 5 Tesla. That is absolutely the right answer. Got it? Perfecto. That is the D option. Everybody understood till this point? Shall we go ahead to the next question? So it's all geometry over here, which you need to solve. So triangle is usually the most trickiest, but if it is a square or hexagon, it is actually very simple. Like for example, this is a polygon of 6 sides, bending of 4 pi meters length. Electric current is also given. Find the magnetic field at the center of the polygon in 10 to the power minus 7 Tesla. So let's do this particular question. It's a hexagon, okay? So it's a hexagon. So if you draw the hexagon properly, things will be clear. Oh, what is this? Okay. This is your hexagon. Now we'll choose any one side of the hexagon. Let's say I choose this side, and I will also draw the end points connecting till the point where we want to find the magnetic field. Okay, next is drawing the perpendicular, of course. Let's draw the perpendicular over here. Now it is given that the perimeter of the hexagon is 4 pi meters. So think about it carefully. If the perimeter is 4 pi meters, what will be the length of a side? It will be 4 pi divided by 6 number of sides are there. So 4 pi by 6, which is 2 pi by 3 meters. 2 pi by 3 meters is the length of a side. Okay. Now, if I assume each side length to be A, even these dotted lines which I am showing will be also A. In fact, all small equilateral triangles are formed. 6 equilateral triangles will be formed. That's property of the hexagon. Okay. Even this angle I know already now. Think about it. It's not that difficult to figure out how much this angle will be. This is 60, this is 90, that will be 30 degrees each. So each angle is 30 degrees. Only thing left is how much boss is this particular distance. So that distance is nothing but the altitude, and the altitude is nothing but the hypotenuse cos 30. Hypotenuse cos 30. The side length, we just figured it out, it is 2 pi by 3. So just put 2 pi by 3, which is the side length. Cos 30 is root 3 by 2. Cos 30 is root 3 by 2. Okay. Everything is coming from here. The wire length is 4 pi. You are bending it into a hexagon. So each side will be this many meters. So altitude will be into root 3 by 2. So 2 cancels and root 3 cancels. So it will become pi by root 3 centimeters. Is it in centimeters or meters? Oh, sorry, it is meters. So then this will be also meters only. Is this? Okay, this will be meters. Okay, distance is known. Now let's figure out what is the magnetic field due to one side. It will be mu naught by 4 pi I by d sine 30 plus sine 30. Is that right? Sine 30 plus sine 30, both the sides. Okay, that's it. So mu naught by 4 pi 10 to the power minus 7. What about the current? Current is 4 pi root 3. Current is 4 pi multiplied by root 3. What is the distance? We just got it over here. It is pi by root 3 and sine 30 is half. So basically, it will be nothing but 2 multiplied by half. Half plus half. Anyways, 2 will cancel. Pi and pi will also cancel. So I am left with 10 to the power minus 7. 4 is left. Root 3 is there. And also that root 3 is there. Root 3 into root 3 is 3. 3 4s are 12. So 12 multiplied by 10 to the power minus 7 Tesla. That is the field due to one side. We have to find the net magnetic field. So there are 6 sides. So 6 into 12 into 10 to the power minus 7. These are the number of sides that I need to multiply. So 12 6 are 72 into 10 to the power minus 7 Tesla. That is the answer. 72 into 10 to the power minus 7. Is this absolutely clear, my dear warriors? Everybody with me? Yeah? 72 into 10 to the power minus 7. So that was the answer. Perfecto. Amazing. So it all starts with over here. Like I said, all these generic questions, you take a side, figure out the field and multiply it by the number of sides. You might use some geometry. Only when you have these questions, the answer is always 0. So I'm not doing a separate question. Whenever you see current entering and exiting, then it is 0. But if it is trapped in a loop, then it is not 0. It will be like this. Okay, how we solve this question like this. Perfect. Now let's go to the last part, which is magnetic field due to a coil carrying current. Yeah, due to a coil carrying current. It's simple. In these cases, if the coil is circular and the current is like this, curl your fingers in the direction of the current. The thumb points in which direction the magnetic field is. Very, very crucial. So your fingers of the right hand curl in the current's direction. Current direction, you curl the fingers. Then the thumb which is there points in the direction of the field. The thumb will point in the direction of the magnetic field. That is the thing. It's very easy to figure out how much is the magnetic field due to a coil carrying current. I mean, just think about it. See, if this is a coil carrying current, if this is the current over here, then if you take any element, if you take any element at the center, at the center, this particular small element, let's say I call it dl, will give me a small magnetic field. Dl cross r will go upwards, so it will give me a magnetic field like this. So this will be a small magnetic field like this. Okay, there will be a small magnetic field like this. Now you take any element anywhere on that coil, no matter where that element is, no matter where that element is, whether it is here, 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 or anywhere, you will say every single time you draw R, and you do dl cross R, that dB will just be in the same direction. That dB will always be in this direction only. So they will all add up, no matter where you take that element. No matter where you take that element, those dBs will add up. So the fields due to all will add up. It will add up. So the net magnetic field is just a simple summation. So the net magnetic field at the center of the coil is a simple summation. It's an integration of dB, which is integration of mu naught by 4 pi I by distance. Distance is the radius of the coil in this case. Radius of the coil in this case. And every time, look at it, the angles are 90 degrees. Can you see that? The angles are 90 degrees, guys. So it will be sine 90. Sine 90. And of course, dl is also there. I dl sine of 90 degrees. Sine of 90, we all know, is the number 1. I is a constant, r mu naught 4 pi, everything is a constant. So mu naught by 4 pi comes outside with the current. Of course, with r also being a constant, being the radius. Only thing left inside is dl. dl is the small length. If I integrate it, it will nothing but be the perimeter, which is 2 pi r. So I am just getting mu naught divided by 4 pi. I is there over here. And oh, sorry, I forgot r square. I'm using Biot-Savart's law. So mu naught by 4 pi I by r square dl was there. So I forgot that r square, my bad. So just keep that r square here. R and r will cancel. 2 pi and 4 pi will also cancel. And I will definitely get mu naught I divided by 2r. So that is the magnetic field at the center of the coil. That is the magnetic field at the center of the coil. Is this clear, everyone? Mu naught I by 2r. There is no pi here. Be very careful. 2 pi and 4 pi cancel to give me 2 at the center of the coil. Perfect. So, what about if I'm not at the center? Sir, what if you are on the axis of that coil? Fine. If you are on the axis, there is again a derivation, not important, but just telling you what the answer will be over here. I've done that in the derivations class. You can find it in the CBSE lectures and everything. So again, this is a wire which is carrying some current, and I want to figure out what is the magnetic field at this point on the axis. This is basically called as the axis of the wire. That answer will be mu naught I divided by 2, just like this, mu naught I divided by 2. Dimensionally, length should be there below. So here you will get r square plus x square, whole thing raised to 3 by 2. And over here, just the number r square. Dimensionally, this is r square on the top. Raised to 2 raised to 3 by 2 means raised to 3. So raised to 3 and raised to 2. Square will cancel. Dimension of length will remain below. That is perfectly fine. So that's how I verified the formula mentally. So this is the answer of the magnetic field. Mu naught I r square by 2 r square plus x square raised to 3 by 2. See, in the same formula, if you put if x is 0, that means you are at the center. You are at the center of the coil. That is right over here. If you substitute x as 0, r square raised to 3 by 2 will become r raised to 3. R raised to 3 and r square will cancel. You will get mu naught I by 2r. So the magnetic field will just be mu naught I by 2r, exactly what you got over here. So this verifies this formula. It verifies this formula that a special case is the center. But in general, away from the plane of the coil, this is the formula. Is this absolutely clear? Let's do some questions coming up on your screen. First question, two circular coils carrying currents in the directions, find the magnetic field at the center. Due to this wire, which one? Due to this wire, which is carrying current, curl your fingers in the current, the thumb points the direction of the magnetic field. So the magnetic field is obviously upwards. Due to this current, which is going like this, curl your fingers in the direction of the current, the thumb points the direction of the magnetic field. So the magnetic field is like this. Currents are the same. Wire radiuses are the same. So the magnetic fields magnitude wise at least are the same. Like this one will be mu naught I by 2, what is the radius? A. Here this is also going to be mu naught I divided by 2A. They are mutually perpendicular, guys, to each other. Yes, because the coils are perpendicular. So what will be the net magnetic field? Can you guys now guess it? Very easy to guess it. So the net magnetic field will be root 2 times any one field. Yeah, use Pythagoras, vector addition, this square plus this square under the root. Both are the same. So root 2 times the side will be the hypotenuse. So it will be root 2 times mu naught I divided by 2A. So root 2 cancels. So it will become mu naught I by root 2 times of A, which is obviously B option. B for your whatever, IT Bombay, you can say. Got it? Very simple. So these kind of questions again very common. Then another type of question which is related to the axis of the loop. A circular loop carries some current. The magnetic field at the center of the loop and the distance r from the center of the loop is in the loop. The formula goes like this: mu naught I r square divided by 2 times r square plus x square raised to 3 by 2. Now here in the question, you are at a distance r from the center. That means x is equal to r. So put r over here. So mu naught I r square whole thing divided by 2 times r square plus r square raised to 3 by 2. Okay, so this will become mu naught I r square whole thing by 2. R square plus r square is 2r square. So 2 raised to 3 by 2 and r square raised to 3 by 2. If you are not able to understand it, it's okay. We'll do one thing. We'll put 2r square whole thing raised to 3 by 2. So what will this become? Observe carefully. It will become mu naught I r square is there. 2 is also there. 2 raised to 3 by 2 is there. R square raised to 3 by 2 will become r raised to 3 because by 2 and into 2 will cancel. Yeah, 2 and 2 will cancel. This is not that difficult now. So this is mu naught I. R square and r cube will cancel. So only r is remaining. What about over here? So this is nothing but, what do you say? 2 raised to 3 by 2, no? 2 raised to 3 is 8. So it is nothing but 8 raised to half. 2 raised to 3 is 8. So 8 raised to half. So this will become mu naught I divided by 8 raised to half means root of 8, which is 2 root 2. So 2 multiplied by 2 root 2 and there is r over here. So that is the magnetic field on the axis, but they are asking you the ratio of it. So they are asking you what is the ratio of it. So let's think carefully. What will be the answer? So first on the center, which is mu naught I divided by 2a or 2r basically, and the whole thing divided by mu naught I divided by 2 multiplied by 2 root 2 r. Okay, mu naught I, r, 2 cancels. So what am I left with? Nothing on the top. And over here, what am I left with? Just 1 upon 2 root 2, which goes on the top only as 2 root 2, 2 root 2 divided by 1. So 2 root 2 divided by 1, which is B option, perfectly fine. 2 root 2 divided by 1. So magnetic field at the center versus magnetic field on the axis. That's it. That's the answer. 2 root 2 by 1. Perfecto. Amazing. Clear. Very good. Let's move. Due to an arc, what will be the answer? That's the last part. It's a final thing over here. See, we all know that due to a circle, due to a complete loop carrying current, the magnetic field at the center was mu naught I by 2r. Okay. What if I have to figure out the contribution only due to a part of the wire? Imagine there is an arc carrying some current. Imagine there is some arc which is carrying some current. It's subtending angle theta. I think it is unitary method. If entire of 2 radians contributes to this much field, how much contribution will be there by theta radians? Unitary method, that's it. So the magnetic field due to the arc will be how much ever magnetic field is contributed by the entire loop. You calculate it per radian, which is by 2 pi, and then multiplied by theta radians. That's it. The entire loop into theta by 2 pi. Does that make sense? Because if the entire loop gives me this much, so per radian, that means by 2 pi, into theta radians will give me the contribution due to that arc. That's it. I hope this is clear. Everyone with me on this? So hence the answer should be magnetic field due to the arc will be, substitute everything over here. Okay, you don't have to remember this formula. If you know unitary method, you can easily do this. Mu naught I by 2r and divided by 2 pi, and then you of course have theta over here. So technically this will just become nothing but mu naught by 2 2s are 4, so 4 pi, and then we have current divided by r, and then we have theta over here. So that is the magnetic field due to an arc of wire carrying some current. Arc of wire carrying some current. Clear about this? Everybody with me? Understood? Okay. Let's see a question coming up on your screen. Here it comes. There is a diagram. Question is figure out how the current is producing the magnetic field at the center. Now there are a couple of ideas in this question. First idea is, if you consider this wire or this wire, this point is on the axis of that wire. And I told you at the beginning of the class, where did it go? Long time back. Oh my God, really long time back. Somewhere here. Magnetic field on the axis. Somewhere I have told you this. Oh, here, correct. Magnetic field on the axis. If you are in front of the wire, the field is 0 because R cross L will be 0. The cross product will become 0. So if you are directly in front of the wire, the cross product of both of them will be 0. So there will be no contribution only. So hence, they will not contribute. So the straight wires contribution is 0. Straight wires contribution is absolutely 0. So forget about it. So the only part which I have to concentrate on now is this particular part, which is nothing but an arc carrying current. How much angle does it subtend at the center? It's a semicircle, so it will be pi radian, of course. So that's the angle. So the net magnetic field will be the magnetic field due to the arc. And I just gave you that formula, mu naught I theta by 4 pi r. So it is mu naught I theta by 4 pi r. So mu naught by 4 pi is 10 to the power minus 7. The current is 3 amperes. Theta is pi. Whole thing divided by r. The radius of that arc is pi by 10. Pi by 10. Pi cancels. 10 goes on the top, becomes minus 6. And that 3 stays there. So this is nothing but 3 micro Tesla, which is B option. That is absolutely correct. 3 micro Tesla. That's how you can solve these questions. Cool. So we have seen how the magnetic field can be calculated due to an arc. Okay, these kind of questions are again common. We have also seen how to find the magnetic field due to a loop on the axis or at the center, all these things. And of course, due to long straight wires, finite or semi-infinite or even infinite. Cool. So that was Biot-Savart's law and its applications. Next lecture, we'll go to Ampere's law and its applications. Okay. So hope you loved the lecture. The PDF will be available in the description box. Okay, after some time. And the next class will follow up again at 8 o'clock. So make sure you are regular on the channel. So we have kickstarted the magnetism unit. Be there every single time on your favorite Vedantu English channel. Quickly like the video and subscribe. Okay. Thank you so much. Good night, everyone. Thank you for being here. Bye-bye. Take care.